Okay, welcome back everybody to the PALS Algebra and Logic Seminar for 2023. Our first speaker this semester is Žaneta Semanišinová, who's at the University in Dresden, and she will speak to us about complexity classification transfer for CSPs via algebraic products. Okay, Žaneta.
Thank you very much. So first, I would like to thank for the opportunity to speak in this seminar. Yeah, and as was already said, so I'll be talking about CSPs or constraint satisfaction problems, and in particular how we can transfer some complexity classification to actually solve some open problems that appeared in computer science in a different context. And this is joint work with Manuel Wodirsky, Peter Jonsson, Barney Martin, and Antoine Motte. Yeah, so what I want to start with is just what is constraint satisfaction problem for me, and some background on studying complexity, like the dichotomies that are known or that we would like to know. Then we move to like open problems that actually motivated, like why to have a look at particular structures that I will want to talk about. And then in the third part, I will actually talk about the structures that we classified CSPs of, and that was like the main result of what we did. Yeah, so first, I mean, I will have a lot of structures in the talk. Always structure will be a relational structure for me. And this, I mean, there will be some relational signature, usually just implicitly, and the signature will be finite. So, and for what a CSP is, there is a fixed structure with a fixed signature behind, and we always say B, and we always talk about constraint satisfaction problem of B for some fixed structure. And input for this constraint satisfaction problem of B is a finite structure with the same signature, and we ask, is there a homomorphism from this finite structure to B or not? And the example that I guess you all know is when the structure that we take is a complete graph, say on 3 vertices, so that can be represented as a relational structure like with this disequality and 3 elements. And CSP of such a graph is just 3 colorability problem for graphs. And more generally, one could take Kn complete graph on n vertices and get n colorability problem. And this is like a prototypical example of some problem that's NP complete, that is computationally well believed to be computationally hard. Yeah, and so what is already known for all finite structures with finite signature, for that there was long-standing conjecture proved by Bolazzo and Zhuk in 2017, and it says that CSP of this finite structure is either NP or NP complete. And now naturally one would ask, like, what happens for infinite structures? Can we expect something like this? Is there a reasonable class where we can expect something like this? And even sooner than this was proved for finite structure, there was a conjecture from 2011 by Manuel Wodirsky and Michal Pinsker that for reducts of finitely bounded homogeneous structure, this is again the case that there is this complexity dichotomy either NP or NP complete. Yeah, and so if, I mean, just to make it clear what I mean by finitely bounded homogeneous, well, reduct, I guess, is clear. Just we drop some things from the signature. And finitely bounded means that there exists a universal sentence that describes all finite structure that embeds in my structure. So, I mean, this means just like informally speaking, there is some finite description of this structure of what can be embedded in this structure. And homogeneous, or sometimes it's said ultra homogeneous, means for me every isomorphism between finite substructures can be extended to an automorphism. So yeah, and I mean, the whole conjecture is kind of a big challenge to tackle, but we can just focus on smaller fragments and hope to understand at least these. And so what's in the scope and what I will be talking about here in the talk are first order expansions of algebraic powers of Q with order, rationals. And the reason are the applications in temporal spatial reasoning that I want to talk about now. Yeah, so first thing that one could study with this Q and order representation somehow is a concept from spatial reasoning. It's called cardinal direction calculus. And the idea is that the domain is just rational plane, so plane with rational points. And the relations that we have just represent the relative position of the points in the plane. So yeah, for example, I mean, the point is to the north of a point is exactly what you would expect. So it's on the same level like on the x-axis, and it's somewhere higher up on the y-axis. And yeah, all the other relations just mean what you would expect that they do. Yeah, and so, I mean, this is like the base structure with the basic relations, and for cardinal direction calculus, the relations are unions of such relations above. So they are essentially some reducts of first order expansions. Yeah, and so now I would like to talk about open problems that were like, they're luckily not open anymore, but they were connected to this concept. So first I need to say what an Ordhorn formula is. It's a conjunction of clauses that have a specific form that's called Ordhorn clause, and it looks like there's a disjunction of these equalities, and then there is one literal that is allowed to do something wilder. And of course, I mean, this m could be 0 and this literal could be omitted. It's just, yeah, nothing very important. And from 1998, there is a theorem by Ligozat that CSP of a reduct of like cardinal direction calculus, in the sense that relations are unions of these basic relations, that contains the basic relations is in P if and only if the relations can be defined by these Ordhorn formulas, and otherwise it's in P hard. So this was kind of resolved for this like two-dimensional concept. But of course, this is a concept that one could easily generalize to n dimensions and talk about n-dimensional cardinal direction calculus. And from 2002, there was a conjecture by Balbiani and Condotta that the theorem also holds for the n-dimensional case. And what one would like to do is somehow, I mean, be able to study this problem and to study the complexity of the problem. And for this, we need a concept of a primitive positive formula. So formula is primitive positive if it's of the form that we have first some existentially quantified variables and then a conjunction of atomic formulas. Yeah, so just one example here. And the reason why I want to talk about such formulas, well, there are two things. First, I mean, I would like to somehow relate this to this cardinal direction calculus. So we would like to be able to define by primitive positive formulas the relation of this CDC somehow using simpler relations. And the simpler relations will be like coordinate-wise order. So, I mean, by this notation, I really mean like ordered in first coordinate, and anything could happen in the second. And similarly for equality, the other disequality, and so. And so these four relations are definable in the basic relation of CDC by primitive positive formula or PP formula, I will sometimes say, I guess. Because we can, I mean, if x is less than y in the first coordinate, we can say there exists this middle point that's somewhere, I mean, in like x is to the west of it and y is to the east of it, and I mean it's somewhere about here, so we can define it like this, and of course all the other relations that's similar. And this is even simpler from the other side. If we want to take this structure with these four simple coordinate-wise relations, we can always define by a primitive positive formula all the basic relations of CDC. Yeah, and so why should we bother to do this? Well, because there is a well-known result of Jevons that if we have two structures with the same domain, such that every relation of one has a primitive positive definition in the other, then we can reduce in polynomial time one CSP, so the CSP that we can define to the other CSP. So this should already like hint on what I want to do with the cardinal direction calculus. I want to study a simpler structure, Q with coordinate-wise equality and order, and then I will be able to reduce the class or to transfer the classification to understand complexity of CDC. So I mean that's what I said. Just so first order expansions of the C basic structure of CDC are PP definable in first order expansions of this and vice versa. And so the CSPs have the same complexity. If we have complexity dichotomy for one, we can also obtain it for the other, and so on. So actually to prove the n-dimensional CDC conjecture, the thing would be to understand first order expansions or CSPs of first order expansions of such structures with coordinate-wise order and equality. And so now I've finally come to one of the things that appeared in the title. So what is algebraic product? That's just a handy construction that actually where these kind of structures with coordinate-wise relation just naturally arise. So if you have two structures and in general they could have different signatures, the algebraic product is the structure that has product domain, and for every relation from the first signature plus the equality, you have like this coordinate-wise relation. So just obey the rules in the first coordinate and do whatever you want in the second. And similarly for, of course, the second signature. And yeah, so I mean, here just a simple example. It's clear that actually the algebraic product of Q with order with itself is really the structure that I was already talking about. And yeah, so I mean, really the coordinate-wise equalities, coordinate-wise equality and coordinate-wise order is also what you would expect. Yeah, and so I mean, we already know why we want to talk about this, because, well, first, this, of course, could be generalized to n-fold algebraic products. And if we take nth algebraic power of Q with order, we obtain exactly the structures that we know that we want to study to classify the complexity of the n-dimensional cardinal direction calculus. Yeah, so that would be one of the applications, and this wasn't so difficult. I mean, we just PP define structure and other structure, and that was it. But there is another transfer concept that's a bit more involved. And for this, we need to generalize PP definitions. So what's a primitive positive interpretation of a structure, or so of, say, of structure C in B, that is that we take a partial surjection from some finite power of B to this universe of C. And this partial surjection is somehow a guide how to interpret C and B, possibly in higher dimensions. So for every carrier relation R that is defined by an atomic formula in C, and here we say atomic formula and not just from the signature, because we also want to define equality. And we would also like to have a formula for the domain of this surjection, which corresponds to truth in C, because that's a surjection. So the preimage of this relation, if it's regarded as D times K array relation over B, this should be definable by a primitive positive formula. So that's a primitive positive interpretation. And it's quite natural concept. I mean, for example, where we will be actually using this is when I want to talk about closed intervals or with rational endpoints. It's very natural to understand them as pairs of rational numbers where one is less than the other. And if I have some relations over these intervals, I would also like to be able to talk about this in terms of relations on endpoints. Yeah, and so I mean, why PP interpretations? Well, because there is a similar well-known proposition that if we can PP interpret one structure in the other, we can also polynomial time reduce its CSPs, its CSP to the other. So, and this leads me to something that we call complexity classification transfer. And yeah, I guess to understand it is just enough to look at this picture. So we start with two structures, D and C. And yeah, normally we just think of it that somewhere, I mean, one of these structures is somehow well understood, say this C and this further order expansions, we already have complexity classification for those. And we are able to PP interpret this D in C and C in D by some pair of interpretations. And we have even additional properties that the composition of these interpretations is somehow well behaved. It's called PP homotopic to the identity interpretation. And this means that this set here is primitively positive. Is primitively positively definable. But yeah, I mean, there's just some technical condition. We use this as a black box here. I mean, one has to prove this, of course, if you want to use it. And the thing is that if I understand first order expansions of C, then if I satisfy these conditions, there is also this relationship with the same interpretations with some other first order expansions of D and vice versa. So if I, on the other hand, want to classify the first order expansions of D, I take the expansion and I know if I satisfy this condition, there is some C prime that has the same complexity because it's PP interpretable one way and the other. And so I can transfer the whole complexity classification to first order expansions of D. Yeah, and so where can one use this? So a well-known concept that appears in temporal reasoning in computer science is interval algebra. And that we take the universe of all closed intervals with rational endpoints. And we have some 13 basic relations that corresponds to relative positions of the intervals. So for example, one interval starts the other, or they meet exactly at one point. Yeah, and similar relations that, I mean, they overall cover just all the possible options. And these are basic relations. And as we had for CDC, all relations are unions of basic relations. And now for this concept, we can also generalize it to something that then appears in spatial reasoning. And we just take n tuples of intervals. So kind of say in 2 dimensions we have rectangles, and in 3 dimensions we have 3-dimensional blocks. And the basic relations are n-tuples of Allen's basic relations. And all relations are again unions of basic relations. And so this is again something that led to open problems. So first, in 1995, Birkett and Nebel, they had complexity classification for CSPs for Allen's relations, and in particular, all subsets that contain the basic relations. And here again, Ordhorn formulas appear. So such a CSP is in P if all its relations are definable by Ordhorn formulas, and otherwise they're NP hard. And in 2003, there was even complexity classification by Krokin, Jevons, and Johnson for all subsets of Allen's relations. Yeah, and so naturally one does then move to block algebras. And in paper from 2002, Balbiani, Condotta, and Del Cerro, they again conjectured that Ordhorn formulas, or like Ordhorn relations in the sense those that are definable by such formulas, are the unique maximal tractable subset of the relations of block algebra that contains the basic relations. Yeah, so I mean this is very similar situation as we had for cardinal direction calculus. So we somehow, the conjecture was saying that what's tractable, what's in polynomial time, is what's definable by Ordhorn relations, and the rest should be NP hard. Yeah, and so now the question is, can we use the complexity classification transfer that was somehow more involved and should allow us to do more to classify these block algebras, or the CSPs of these block algebras, again using the algebraic products of Q with order? And the question, the answer is yes, because there is this this mutual PP interpretability between the structures that we need for transfer. So yeah, just for illustration, if n is equal to 2, we can interpret the pairs of intervals, so the rectangles, in second power of Q squared, just by restricting the universe, the domain of the surjection, because we know it can be partial surjection, to those pairs A and B where A is less than B in first and second coordinate. And just for the interpretations, we need to shuffle the numbers that we have so that they really form intervals. So we know that A1 is less than B1, so we get them together for one interval, and A2 is less than B2, so we make the other interval from them. So that's one of the interpretations, and the other interpretations is even simpler. They're just one-dimensional. We just take a pair of intervals, and we want to be able to obtain any pair of rational numbers. So we just drop the endpoints and we just keep the starting points, and they of course can form any pair of rationals. Yes, so I mean this is just to give you an idea. How does this interpretation look like? Then one has to prove that really this PP homotopy thing is true. Yeah, and so for the classification transfer, this was actually talking about classifying first order expansions of some basic structure, but all of the relations, they were unions of basic relations, so they are first order definable in basic relations. Yeah, and as I already said, the interpretation satisfied the assumption for this complexity classification transfer. So we can prove the conjecture as long as we are able to classify first order expansions of the nth algebraic power of Q. Yeah, of course, I mean, also we need to understand what orthogonal formulas do over there, but this is like the idea that we actually want to focus on this type of structure. Yeah, and so I think there was like for the motivation somehow why we should actually be interested in algebraic products. And now comes the more algebraic part, where I would like to give an idea like how we classify the CSPs of first order expansions of the algebraic powers of Q. Yeah, and so as in many CSP classifications, at some point polymorphisms need to come into play. So what is a polymorphism? That's an operation on some. So we have structure A with domain A, and a polymorphism of this structure is something that preserves all its relations in the usual sense. So if somebody brings us tuples from the relations and we apply row-wise the map on these columns, so the result is again supposed to lie in the relation. So for the simplest example almost possible, I guess, is this for Q with order. If we have two order tuples, we can add them and the inequality will still be satisfied. Yeah, so I will need sometimes this notation for the set or clone, if you know what clone is, of polymorphisms of A, this pol A. Yeah, and so important thing why one should actually care about polymorphisms is that this is connected to PP definability, and we already know that PP definability is connected to complexity of CSPs, and even to PP. Polymorphisms are then even connected to PP interpretability and so, but yeah, just to illustrate this, if a relation is polymorphisms of an omega categorical structure, then it's also primitively positively definable and vice versa. Yeah, and so this was like why we should care about polymorphisms, and now maybe a bit more justifications for why we should care about algebraic products. Why is this a good way how to think also about our Q structures with coordinate-wise relations? And this is, the reasons is that they're behaved quite nicely, these algebraic products. For example, if we have two structures that are homogeneous, in the sense that I already mentioned, then the product is also going to be homogeneous. Same for omega categorical. And even more important thing for us, because we want to study polymorphisms, is that the polymorphism clone or polymorphism set is a product set if we take it from product. So if we understand the polymorphisms of the structures separately, we immediately understand the polymorphisms of the product. And this is not just for the product itself somehow, but also for the first order expansions. We just add some relations so we don't lose, we don't get any new polymorphisms. And all polymorphisms will be of the form something happens in the first coordinate, something else happens in the second, and these things don't interact together. Yeah, and so even just like observation to really see that this is behaved nicely, at least if we don't expand, if we have CSPs of both of the structures in P, then the CSP of the product is also in P. And the algorithms are just the simplest that you would come up with. So if somebody gives you an input, this finite structure, you just take the reduct of the for the first signature and for the second signature. Because yeah, so without loss of generality, we could think of the product as being over the union of the signatures. And we can run the algorithm for first CSP of the first structure, and then on second And if both answers are yes, then the answer is yes, and otherwise it's no. Yes, so I mean, for just the product, it's pretty simple. And the question is, what happens if you expand with first order relations? What could go wrong? And on the hardness part, it's already resolved. So, I mean, I guess from now on, if I will have some general structures A1 and A2, they will be countable and omega categorical. And I will need this map theta I that, I mean, from this product clone that we already know that this product is just project on the ith coordinate. And by results from 2018 by Bato, Oberschall, and Pinske, we can understand the hard cases of first order expansions of algebraic products. Because if we take a first order expansion of such product, if it happens to us that there is at least one of the two coordinates where the projection of the clone satisfies some condition that, if you are not familiar with the notions, just think of this as a hardness condition. So if the projection of this clone has a map that's uniformly continuous minus preserving to the polymorphism set of K3 of this complete graph on 3 vertices. So this is somehow meaning that this should be hard in this coordinate in the ith coordinate. Then actually it happens that the whole polymorphism clone of D has such a map to polymorphisms of K3 and the whole CSPs and P hard. Yeah, so I mean, this could seem a little bit cryptic, I guess, but the way how to interpret is really, if CSP over first order expansion of algebraic product is computationally hard in one coordinate, it immediately means that it is computationally hard. So this is what we seen also for just the product. If one of the things answers, if we cannot really compute in one of the coordinates, then the algorithm wouldn't work as I introduced it over there. Yeah, and this is like a proper proof that computationally hard means in one coordinate means computationally hard. And so there is a natural question, of course, if somebody guarantees me that the thing looks tractable in both coordinates, it doesn't have this nasty map to polymorphisms of K3 where it becomes hard, does it already mean that my CSP is tractable? And this is not known like for larger class of infinite structures. We just have some partial answers. So for finite structures, this is already resolved, though I guess no one was really studying it in like using algebraic products. But the idea is, if you have a, so I mean, again, polymorphisms somehow characterize, if you have nice polymorphisms, it should somehow characterize being easy, tractable, and this nasty map to pole of K3 is somehow hardness condition. And so the operation that gives us easy cases in the finite domain case are cyclic operations. So just operation where if you cycle you satisfy the identity that the result doesn't change if you cycle the variables around. And so what is known by results of Bato and Kojic from 2012 is that if you're hard in one of the coordinates, this I, then, sorry, if you are not hard in one of the coordinates, you don't have this UCMP map to polymorphisms of K3, then you have an operation in your polymorphism clone that in one projection is cyclic. And from these two operations, so if we are not hard in any of the coordinates, we have C1 and C2 in first and second coordinate, and we can compose them in this way, and the result will be cyclic overall. And this by results of Boulato or Jouk implies that the CSP is tractable. So for finite domain case, we really know that tractable plus tractable implies tractable. What happens for powers of Q? This is actually what we focus on in this talk. There is a candidate polymorphism, like candidates also for other cases, not just Q with order, but here we also had the expectation that this kind of polymorphism could be the tractability trait, and it's called pseudo-weak near unanimity. And this pseudo-weak NU polymorphisms, they like almost satisfy the weak NU identity. So this f of y of an axis is equal to f of when you shift the y around, and all of these k equalities, but up to modification up to application of some endomorphisms that are fixed for the operation. Yeah, so the question is, if you again, like, will it happen that we can obtain something like this coordinate wise, and can we compose it so that we get it overall? And so for this, one somehow needs first to know what happens in the one-dimensional case, which is already known for quanta sometime by Bodisky and Kara's paper. So if you have a first-order expansion of Q with order that contains such a pseudo-weak NU polymorphism, then the CSP is tractable, and otherwise it has this hardness condition that you have uniformly continuous minor preserving map to polymorphisms of K3, and the result is NP. Yeah, and so what we eventually proved for n-dimensional case is that if you have a first order expansion of this nth algebraic power of Q, then exactly one of the following two cases applies. This doesn't even depend on P versus NP question. If one of the, I mean, if in every of the coordinates you have this polymorphism that should be a trait of tractability, then you actually have like overall this polymorphism and the CSP is in P. And otherwise, and this is what already follows from the result by Bato, Opperschall, and Pinsker, if you are hard in one of the coordinates, then there is no chance and the CSP will be NP. And using the syntactic description of the tractable cases already for like one-dimensional case for Q, we can even I mean, we still need to resolve the all problems. We need to get back to syntactics somehow, because we need to, I mean, we wanted to prove something about defining by odd Horn formulas. But I mean, there are nice syntactic descriptions for the one-dimensional case, and using these. Also, the proof for the algebraic powers is actually quite syntactic. I mean, if I have some, yeah, I'll talk about this in a couple of minutes a bit. Then we can derive what it really happens for the syntactic definitions. And so for binary signatures, which was always the case for cardinal direction calculus, and also Allen's interval algebra, the block algebra, we have one of the following cases. Either every relation has or the Horn definition, if you view it as a relation over Q, and the resulting CSP is in P. Otherwise, you satisfy this hardest condition and the CSP is NP complete. And then using what we've seen with PP definitions, PP interpretations, one, I mean, almost immediately gets the CDC conjecture is true, and that the the block algebra conjecture is true. Yeah, and so let me talk about the remaining time a bit about the proof. I mean, it's quite a lot of technical steps, but there are some ideas I hope that could be extracted. So for empty completeness, there was actually all work done before. So this follows from the result that I already showed you. But for the tractable case, well, first, I mean, how we want to think about our relations, we think about first order expansions. So everything is definable by first order formulas that use this coordinate-wise order and coordinate-wise equality. And our structures have quantifier eliminations because they are omega categorical and homogeneous. So we have definitions in quantifier free and even in conjunctive normal form if we want. So the thing is actually what kind of clauses appear there. And there are special clauses that are behaved nicely. We call them I-determined. So that's just clauses that talk about, so they contain just relations with one index I and they don't mix them up. And this is not something that we could always hope for, but under the assumptions under which we want to prove the tractability, we may restrict to conjunctions of something that we call the weakly I-determined clauses. And they are like an I-determined component. And then in the rest of the clause, there could be attached a couple of disequalities that talks about the other coordinate. So it's not like completely wild situation, but also it's not directly clear what one could do with it. Yeah, and so first, I mean, let's think about what happens for the I-determined case. So if all clauses that appear are I-determined, we can really take our clauses and put those that are one-determined into one group, two-determined into second group, and run the algorithm for the first coordinate that is guaranteed by the theorem for one-dimensional case, and then run the other algorithm for two-determined constraints, and then again just put together the results. If both answers are yes, then yes, and otherwise no. And this is not hard to see that this actually works. And yeah, and so the situation for when the relation has such a nice definition, we actually managed to really understand this in terms of polymorphisms. This is not hard proposition to prove, and it even holds like for general algebraic products. If every relation has such a definition in our first order expansion, then the polymorphism clone of the expansion has to be product. So of its projection to the first coordinate and to the second. And alternative characterization is just having this nice projection combination. Yeah, and so I mean all of the implications are kind of easy to see. So from 1 to 2, yeah, I mean I guess from 1 to 2 this is like most involved. The one inclusion from left to right, the inclusion is clear, and from right to left, one tries to apply the polymorphisms of the relation and use it the syntactic form. From 2 to 3, that's clear because projection is always a polymorphism. And from 3 to 1, this is nicest by contraposition. If you had such a mixed clause, this polymorphism would allow you to violate actually the condition, the relation, because you can take an assignment that satisfies just one of the literals that talks about first coordinate, and assignment that satisfies just everything in the just the literal that talks about the second coordinate. If you have like reasonable assumptions on your definitions, and yeah, that's then you can see that you cannot have a relation that satisfy that it is not conjunction of such clauses. But also what this proposition shows is really that sometimes when we don't have such nice situation in our polymorphism clone that we have these projections, we just might have also clauses that are not I-determined. And so what happens for the cases that are not so nice? So for weakly one-determined clauses, that as I said, this is something that we always have. And yes, so it's not so straightforward as I try to present it here, but just to give you a glimpse of what does the solution look like. The idea is that weakly determined means something determined and then a bunch of disequalities. So we compute pairs of variables that satisfy equality in all of the solutions. And since we know that some of the things will be actually equal, we know that some of the literals or some of the disjuncts in our clauses, they're just useless, and we can modify our weakly one-determined clauses to obtain one-determined constraints. And if we do it carefully enough, then really the result will be still a relation that's PP definable. And so, as long as we obtain really one-determined constraints, we are free to use the polynomial time algorithm that's guaranteed to exist by classification for Q with order. Just the one-dimensional case. Yeah, and so natural question that arises if you think of the definition of weakly one-determined clauses, that's just perfectly fine definition also for general algebraic products, not just for things over Q. So what one could think of, is there again a nice polymorphism characterization that says to us when we can define really everything to biweekly I-determined clauses? This could maybe like help us not to get our hands dirty with the syntactic arguments for the algorithms, and also it could help to understand the algebraic products of different structures. Yeah, and so just to wrap up, I would like to talk a bit about what one could do for next work. So one of the things that we would kind of like to understand is what happened for algebraic products of a finite structure with Q with order, because, well, there are two reasons. One is that this might be good option to actually understand how the algorithm for CSPs for finite structure actually works, because this is still not kind of really well understood. And also all of these kind of structures, they fall into scope of larger classification problems of CSPs of all structures that are first order interpretable over Q with order, which would be again a nice class to understand if the complexity dichotomy that is the subject of this Podolsky-Pinsker conjecture holds or not. And another thing that's more about algebraic products is to say, okay, let's believe Podolsky-Pinsker conjecture. Can we then say something about algebraic products of structures that are finitely bounded homogeneous? And the good news is that we already know what happens for hardness, because this is the result that I already mentioned a couple of times, that hardness in one of the coordinates already implies that the result is hard. What remains is the case where we know that both of the things are tractable, and we are interested in the result. And yes, so for the general problem, of course, one would have to make the solution way less ad hoc, not just to combine specific properties of the algorithms, which is something kind of that we needed for this Q with order, but to really understand like what does it mean in terms of polymorphisms and so. Yeah, and I guess that's what I wanted to say. So I would like to thank you for your attention. And if there are any questions, I'll be happy to answer.